Now, there's one more concept that is definitely worthwhile elaborating, and it has to deal with the body cavity. Up here, we talked about these simple-bodied platyhelminths. I basically pointed out that there's no body cavity whatsoever in these animals. And I want to clarify what that means and why body cavities are important. All right. So by body cavity, I mean not the digestive space. This would be the fluid-filled space that accommodates all of your internal organs. I mean, if you were to open up your body cavity, you would be able to see your liver and your stomach and your intestines and your lungs floating around in this fluid-filled space. The space, it's that empty space between the body wall and the internal organs that is the body cavity or the coelomic space. Okay. Now, the coelom is, after all, important. We can't ignore the coelom as a topic for discussion in Bio 202. For one, it is the space that accommodates the internal organs, which is enough on its own, but it's actually kind of closely related to the evolution of larger body size. The larger an animal becomes through evolution, the more it's dependent on internal organs to provide the additional surface area for the exchange, for example, food from the digestive space into the bloodstream, or for the elimination of waste, or for the uptake of oxygen. Basically, we have all these internal organs because we can't rely on our external surfaces to carry out those functions. Right? If you're small enough, if you're a really tiny salamander, you don't even need lungs. You could breathe through your general skin. Salamanders that are above a certain size, however, require an extension of their surface area. Their skin isn't enough, so they have internal spaces, and we call them lungs, that allow them to exchange gases with the outside world. Right. The other thing that a coelom does is that it provides a fixed volume of non-compressible fluids that allows the animal to have what's effectively a hydrostatic skeleton. Okay. Now, the concept of a fluid-filled space being the same as a skeleton is a little weird for some people, and it requires some getting used to. I mean, what does a skeleton do? It does two things. It holds our shape. It helps us maintain a shape. Now, if we're talking about a normal skeleton that's made of hard parts, we're talking either about an endoskeleton like our bones or an exoskeleton like what you find in insects or crustaceans. And this is important for not only holding our shape, but also allowing us to move around. We move by having our muscles move around our bones. And wherever our bones go, the rest of our body goes. It's kind of like we get around our world by causing our skeletons to move in the way that we want them to. Okay? And this brings up the question, I mean, how does an animal without a normal hard part skeleton, how does a soft-bodied animal move around, right? Now think about it. Okay, so if this is your arm, here's your humerus. Okay, anatomically correct. You can tell because I'm putting little knobs at the end. And here's your ulna, and here's your radius. Right, so your hands up here. Right. How do you raise your arm? Well, you've got a muscle. You've got a biceps muscle on this side, and the biceps muscle is going to attach to the lower arm, the forearm, and by contracting here, you're causing your arm to move in this direction. By contracting the triceps on the other side, which attaches in this direction, by contracting on this side, you're causing the arm to straighten out. Basically, these muscles are making you move around by causing the bones to move, right? So imagine yourself as a worm, okay, and you got this muscle, these muscles on this side of your body. These are muscles that go in this direction. You got muscles on this side of your body, and this might be these are longitudinal muscles. They run in the same direction as the worm. Okay, so if this is your wormy body, right, and inside the wormy body you've got a fixed volume of non-compressible fluid. What happens is that if you were to contract these muscles, okay, if you were to contract these muscles, the worm would have to shorten. Okay? You would have to have the animal shorten up. But because there's a fixed volume of non-compressible fluid on the inside, as the animal shortens, it would also have to get really thick. And so now we've made the worm much shorter, but it's become a lot thicker in response. It's become thicker. Okay? And then presumably we'll have another set of muscles that are going to run in this other direction, circular muscles that run like this, that can contract. And basically, if we contract these muscles, we can basically go back to being long and thin again. Okay? And so the way that worms work is that they cause their bodies to thicken and lengthen and thicken and lengthen. And this allows like an earthworm to crawl along a sidewalk. I'm sure you've watched them do this in the past. They stretch their bodies out, they grab hold of the sidewalk, and they pull the rest of their bodies along. Okay? And so, in effect, this non-compressible fixed volume of fluid is operating like a skeleton. It gives the muscles something to work against, to press against, causing the rest of the worm's body to move. It's creating movement as a result of contraction of muscles. It's actually pretty difficult to cause muscular movement in the absence of something like a hydrostatic skeleton for soft-bodied worms. And so yeah, the coelom is important for these reasons, right? And I'm not going to argue with that. Nobody's going to give you an argument about that. Now, what the coelom is not terribly important for is it's not a very good key for understanding the phylogeny of animals. Okay, we used to think that it was. So back in the day, there was this old school idea that the earliest animals had to be the simplest ones, and the latest animals had to be the most complex. Okay? Those animals that were kind of in between would be intermediate in complexity. And the obvious sequence for people would be that the earliest forms would have to give rise at some point to these intermediate forms, and the intermediate forms would eventually evolve to have greater complexity, and those are the ones we find at the end of the process. Now, in this old school picture, these earliest simple animals were the ones that had no coeloms. Okay? No coelomic cavity whatsoever, no body cavity. And if you look at flatworms today, they don't have any body cavities, so the inference was that if you look at flatworms, they were evolving from this basal ancestor that had no coelom. It never had a coelom. Basically, it represents a position at the very bottom of the bilaterian tree. A little bit later on, we've got partial coeloms, and we have animals today like nematodes have partial coeloms. We call them pseudocoelomates. They kind of represent an intermediate position in this old school tree. And so we've got the flatworms. We call these acoelomates, acoel, to represent the fact that they've got no coelom whatsoever. We've got the pseudocoelomates, including the nematodes and a few other animal phyla. And then you got everybody else. Basically, the eucoelomates, eu meaning true coeloms, or true body cavity. These are the ones that include everything else. Basically, the protostomes and deuterostomes would have been in the eucoelomate taxa. And what this means is that in this old school picture, protostomes and deuterostomes did not include the nematodes of the flatworms or any of the other pseudocoelomates or acoelomates. They only consisted of the things that actually had true coeloms. We're basically putting the presence of a body cavity in as one of the most important determinants of where an animal belonged in the overall tree of life. And I want you to realize that this old school idea is totally wrong. We know that this is the wrong idea, and so we compare this with our actual picture of the tree of life, which we have up here. We realize that up here at the very top, we've got the platyhelminthes, acoelomates. They're actually within the Lophotrochozoa, within the protostomes. We've got the nematodes over here. Those are actually pseudocoelomates, and yet they're within the protostomes as well. Okay, and so having said that, I guess the other part of the question is, well, if that's not a good way of describing things in terms of saying, well, we've got the acoelomates, the pseudocoelomates, and the eucoelomates, what kind of validation can we offer to put together the organisms in the way that we've put them together here? For example, why on earth would we ever think that it would be a good idea to put the arthropods and the nematodes together? It seems like the arthropods actually look more similar to the annelids, right? They both got segmented body plans. They both have appendages. Annelids don't have jointed appendages, but they both have segments and appendages on their bodies. Why don't we have annelids and arthropods together? In fact, that's kind of like the old school picture as well. Instead, we're putting arthropods together with the nematodes. And why do we do that? Well, I guess, first and foremost, the reason is molecules. We can use molecular data to pretty much confirm beyond any reasonable doubt that arthropods and nematodes are sister taxa. Arthropods are far more closely related to nematodes than they are to the annelids. Okay, but apart from molecular similarities, it's not like we can name a whole taxon based on some sequences of A's, C's, T's, and G's. And so what we have to do is we have to look for some characteristic that'll bring these guys together. And what we've come to is the idea that all of these guys in the ecdysozoa, they share the common characteristic of shedding cuticle, shedding their outer relatively rigid coating, their skin. Right? And that process is called ecdysis, shedding of cuticle. And the term ecdysozoa basically means animals that undergo ecdysis, animals that shed their cuticle. And this seems to be a common theme that unites animals like arthropods and nematodes, as well as some other things like the velvet worms and the tardigrades. They all seem to have the same property. Okay. Now, if we look at this other group over here, platyhelminths, annelids, mollusks, they seem to be equally diverse. I mean, annelids have segments, mollusks don't. Mollusks have mantles and mantle cavities, annelids don't. Flatworms don't even have a coelom. What is it that could possibly unite these guys? And similar to the ecdysozoa all sharing ecdysis, Lophotrochozoa all share at least some kind of unit, some kind of body unit that has cilia. And so we've got the trochophore larva in the case of something like an annelid or a mollusk. And in the case of other members of this, in the case of other organisms, we've got some type of lophophore, which is a feeding apparatus used by the animals to draw in nutrients. Okay, let's see if I could find some pictures of a trochophore larva for you guys. Okay, so now here's a slide from my normal lectures that I'm particularly happy with. For one, it actually allows us to kind of picture what goes on between protostomes and deuterostomes. So you can actually see from this that there's a blastopore right here and a blastopore right here. These are both basically gastrula larvae. And from this gastrula larva, we're going to create a full-on gastrointestinal tract with a mouth and an anus. And so here's a larval stage for the worm that we have down below. We've got an errant annelid worm. And on the right-hand side, we've got a hemichordate worm. It's called an acorn worm sometimes. But if I scroll this back up, you can actually see the process of mouth-anus polarity orientation formation from the blastopore. And in the case of the protostome, the one on the left, the blastopore actually becomes the mouth. The structure at the top of the blastopore becomes the mouth, and the blastopore actually stretches out. And in this errant worm, the blastopore is also becoming the anus. However, in the deuterostome, you can actually see that the mouth is cutting open. There's a second opening from the archenteron, the space inside the gastrula. It's opening to the outside, and that's going to become the mouth of the animal, and the anus is down on the other end, which is basically the derivative of the blastopore, right? Now, what's really kind of crazy about this is that even though we kind of start off and end up at pretty much the same points. They're starting off as gastrulae. You're ending up with these little ciliated larvae that have a mouth, an anus, and a gut in between. The mouth and the anus are deriving in different ways in the protostome and the deuterostome. And even though these organisms, they start off as gastrula, they actually ending up like worms. They're not related at all. This is kind of like a grand coincidence. And the other thing about this is that you can actually see that this larva on the left-hand side has got a lot of cilia that surrounds the feeding region. This whole structure here is the trochophore, and all the cilia in this structure will sweep the food towards the mouth, which will then allow the animal to eat. You pretty much have a very similar type of structure in the deuterostome worm. But but you wouldn't call this, I mean, you could probably call it a trochophore, but it's not in the Lophotrochozoa because it's not even a protostome, right? Skip down a little ways. Lophotrochozoa are those animals that have either some type of trochophore larva, which is kind of like what this uh, embryonic worm looks like after 24 hours. It actually grows into a metatrochophore, and then eventually it metamorphoses into something that looks like an adult. This is the trochophore larva that we see in the life cycle of the errant annelid worm. If you look at the bottom, you've got a lophophorate. This is a bryozoan that has this tentacle-lined feeding structure, and it's kind of shaped like a little horseshoe. And all the cilia on these tentacles sweep the food toward the mouth of the animal. It's basically feeding in the same way that the trochophore larva is feeding in the worm embryo. Right. In contrast, something like the scorpion, it uses ecdysis as a means of growing. The cuticle, the exoskeleton, is basically a hardened version of the cuticle. It's rigid. It doesn't expand. It doesn't stretch out. So in order for the animal to grow in size, it needs to shed the old cuticle, which is a little bit smaller, and then expand the cuticle before it hardens into an exoskeleton, before it becomes rigid and not expandable. And so these animals in the ecdysozoa have that characteristic. It's kind of an ad hoc thing that, yeah, scientists added these terms to accommodate the fact that we have a bunch of organisms that we now need to put together. All of these lovotrochozoans, platyhelminths, annelids, and mollusks, we have to put them in the same category, and we need a term to describe them all. And it seems like they all have this characteristic of ciliated feeding structures, and they don't have ecdysis. It's important as well. The ecdysozoans, they all have ecdysis, and they never have any ciliated feeding structures. And so that allows us to create two clean, separate groups within the protostomial lineages. And now thinking about both of these groups, but especially the ecdysozoans, okay, we think of them as having harder outer parts. We think of them as needing that ecdysis in order to grow. Both of those characteristics, both large body size as well as hard body parts, are things that we associate with animals that are capable of leaving really good fossils. Some of our best early fossils are arthropods and things with shells like mollusks. And this is kind of like the hallmark of some of the earliest animals of the Cambrian, right? Remember that all of these animal phyla, from platyhelminths all the way to the chordates, they make their first appearance in the fossil record during the Cambrian, which is the first time of the Phanerozoic. While any of these bilaterians from the Precambrian would mostly have gone unfossilized. The one exception to this might have been something like Kimberella. And that's presumably because they're both small, and being small, they didn't have huge numbers of predators, and they tended not to have hard body parts. The difference between the Phanerozoic and the Precambrian is, as you might remember, an uptick in O2 oxygen. We go from something very close to zero all the way up to a grand, roughly 2.1% atmospheric oxygen, which was really substantial. I mean, it's nothing compared to what we have today. Today we've got about 21% oxygen. It's roughly about 10 times as much O2 compared to what we had during most of the Cambrian. But 2.1% is really huge compared to what we had before the Ediacaran Cambrian break. And for that reason, it allowed animals to grow larger. It allowed animals to develop harder body parts. And in doing so, we basically were able to launch into the Phanerozoic. Okay, so the next lecture is coming up, not this one. We're going to be starting to talk about the phylum Chordata, which is our phylum. We like that group.